Hi everyone, welcome back to the Runtime Diaries. I am super excited to have you all here for day 4 of Educative's hashtag 30 Days of Code Challenge. So today we are going to be solving single element in a sorted array problem. This one's super fun, so stay tuned and watch the breakdown with me. Here's what the problem gives us. We have a sorted array where every number appears exactly twice, except for one unique element. Our job is to return that single number. The array is sorted in non-decreasing order. There's always one unique element, and n is odd. The goal is to solve it in O log of n time or less, and O of 1 space, which immediately tells us binary search will be involved. Let's look at a few examples. Example 1. We have an array from left to right, 1, 1, 2, 3, 3, 4, 4, 8, 8. The output is 2. The pattern of pairs breaks right at index 2. Example 2. From left to right, we have our array 3, 3, 7, 7, 10, 11, 11. The output is 10. The pairing flips just before index 4. And in edge case, just an array with 1. The output is 1. With only one element, it's already unique. My first instinct was right about using binary search because the array is already sorted. But I was focused on values, not positions. I tried things like XORing all the numbers or checking sums, but those are O of n. Binary search on values doesn't help either because duplicates confuse the ordering. The breakthrough question here was, what does a perfectly paired, sorted array look like? Without a single element, every pair starts on an even index. 0, 2, 4, 6. When we insert a single number, that structure flips. From that index onward, pairs now start on odd indices. So the single element acts like a pivot that flips the parity pattern. That's our clue. We can binary search for where the pattern flips. Here's that flip visually. Before the single element, pairs are aligned on even indices. After that, pairs start on odd indices. So, our binary search goal is to find that first misalignment, the moment the even-odd pair pattern breaks. We can express this as pseudocode. Compute mid. If the pattern is still correct, move right, otherwise move left. For the parity version, if mid is even, compare mid and mid plus 1. If mid is odd, compare mid and mid minus 1. Wherever this pattern fails is where our single element lives. Here's the first working version. I'm using standard binary search with 2 branches, one for even, mid, and one for odd. It works fine and runs in O of log n time, but it duplicates logic and is a bit clunky to read. This is often the "it works but feels messy" moment in coding, the perfect place to look for optimization. Even this naive version is already O of log n time and O of 1 space because we keep cutting the search range in half and using constant extra memory. But notice the branching duplication. That's our hint that there's a more elegant structure hiding underneath. Here's the question I asked next. Can I remove the parity branches? Bitwise operations gave the answer. In binary, even indices end in 0. Odd indices end in 1. Using XOR with 1, I XOR 1 flips that last bit. So you have your pairs 0 and 1, 2 and 3, 4 and 5. Each flip takes you to the pair partner's index. So, nums of mid XOR 1 is always the neighbor in the pair. That's a single line replacement for our entire even-odd branching. Here's the final version of the solution. I bound locals at the top for speed and clarity. ARR equals nums, ARR underscore get equals ARR dot underscore get item underscore. Inside the loop, I compute mid and the pair mate index with mid XOR 1. If the pair is still intact, ARR underscore get mid equals ARR underscore get pair mate. We move right. Otherwise, the pattern broke, so we move left. The loop ends when low equals high, and that's our single element. A few Python-specific tweaks make this tight and efficient. Local binding, ARR equals nums, prevents repeated name lookups. While low less than high simplifies our loop control. Strong invariant comment reminds you of the rule. Fully paired prefix, going to array of I equals array of I XOR 1. When that fails, the single lies left. Clean logic and documented invariants make your future self thank you. The optimized version is still O log of n time and O of 1 space. But you can't go faster than this. Each comparison tells you which half to keep. That's the mathematical limit of binary search. You've hit the theoretical lower bound. A few lessons to keep in mind. A sorted structure lets you search by position, not value. Binary search is really pattern recognition, not just division and midpoints. Bitwise tools like XOR 1 simplify pair logic beautifully. Always look for the flip in structure, not just the number you see. From confusion about values to recognizing the pair pattern, from branching logic to an elegant bitwise solution, from working code to optimized clarity. Sometimes the biggest optimization isn't in your code. It's in how you see the problem. And that's a wrap for day 4. I hope you learned something new, from bitwise operations to binary search. There were some really interesting topics in there. So stay tuned for day 5 coming up, and we'll see you then.